hear you. They'll hear you okay. They'll be quiet. Let me just turn my phone off. I just realized that the phone... Okay. Okay. Ladies and gentlemen, welcome. Thank you for coming in such a huge turnout. This presentation will be both in Croatian and English. I will do the Croatian part because it's intended for the students and the people here. And then our presenters, we have two, Professor Adriano Kamps and Engineer Dimitro Ogorodnik. Professor Kamps has launched several satellites up to now. Will tell us about his experiences. And Dimitri here works for a company that launches and builds satellites. And then I will first show you what we do at FER, and that's going to be in Croatian. And I'll wrap up. I have 10 minutes, so let's get going. Dobili smo financiranje od Hrvatske zaklade za znanost da napravimo satelit veličine 1 CubeSat. Pokazat ću vam kako to izgleda. I tražimo studente koji se žele uključiti u taj projekt koji će uključivati izradu, lansiranje i korištenje satelita. Što je CubeSat? Vjerojatno ste čuli. Mali satelit, ovakve veličine, 1 kila, malo više od kile, 1 litra, koji ima standardni format, tako da se cijena lansiranja i razvoja je u stvari relativno mala. 100.000 eura je dovoljno da se napravi, daljnjih 100.000 eura je dovoljno da se lansira. Dakle, u principu su to brojke koje uglavnom sveučilišta u svijetu su u stanju financirati. Tako da tih satelita danas ima u svemiru na stotine. Čuo sam jučer od Dimitra da su oni prošle godine, 2017. poslali 100 satelita u svemir. Jedno od pitanja koje dobijem, koliko traje taj satelit kad se pošalje u svemir. On ovisi o tome koliko visoko ide. Svi idu u low Earth orbit. To je u stvari sateliti idu do 650 km, a razlog tome je da ne smiju ostati u svemiru dulje od 25 godina. To je dogovor između velikih svemirskih organizacija koje kažu da ne želimo smeće u svemiru. Ova ovdje krivulja pokazuje koliko vremena je očekivano koliko će satelit trajati u svemiru. Mi ćemo vjerojatno slati na 500 km, znači da će biti gore otprilike 2,5 do 3 godine. Komponente ovog projekta su 3, ja sam ih podijelio u 3. Imate izradu satelita, izradu zemaljske stanice, lansiranje satelita i konačno kad je gore u svemiru morate nešto s tim raditi, jel tako? To se zove payload, funkcija. Šta će satelit raditi sljedeće 2 godine? To je u stvari cilj našeg HRZZ-a. To zovem operativnom fazom gdje treba primiti podatke, analizirati, raditi znanost iz toga. HRZZ nas financirao za ovaj dio i ovaj dio. Na ovom financiranju još radimo. HRZZ traje 4 godine. Od čega se sastoji CubeSat? To je jedan autonomni sustav. Kad ga pustite u svemir, on pasivno putuje. I ne možete ništa, prvo ne znate gdje je, to morate skužiti. Ne znate kak je okrenet. Treba biti u stanju kontrolirati svoju orijentaciju da bi slikao zemlju i poslao signale. Mora komunicirati sa zemljom i napaja se sa solarnim panelima, ima bateriju. I jasno, radite svoj payload, funkciju koju treba satelit raditi. Konačno imate mikroprocesor koji mora upravljati svim time. Na sebi ima software i kontrolira podsustave i podatke. Naša primarna funkcija, ima ih 5, pokazat ću vam koje jesu. Naša primarna funkcija je mjerenje svjetlosnog onečišćenja. Ovo je znanstvena funkcija jer HRZZ nam je dao novce zato da napravimo nešto znanstveno, da imamo znanstveni doprinos. Oni ne financiraju inženjerske projekte, a izrada satelita je većinom inženjerski projekt. Konvencionalne natrijeve živine lampe, ono što svijetli po po ulicama, ono žučkasto svjetlo, se uglavnom sada zamjenjuje u cijelu svijetu sa LED rasvjetom. Naše pitanje je jel se može iz svemira procijeniti koliki je udio te LED rasvjete. To ćemo napraviti tako što ćemo snimati zemlju i onda ćemo implementirati algoritam koji će tu separaciju napraviti. To je samo prvi i glavni projekt. Ima još 4 osim toga. Mjerit ćemo geomagnetsko polje globalno, izmjerit ćemo promjenu gustoći i energiji elektrona u ionosferi. To ćemo raditi jednim novim tipom detektora koji je razvijen ovdje na fakultetu, na Zavodu za elektroniku, koji također može mjeriti i ultraljubičasto svjetlo, pa smo mislili da možemo pratiti gdje se nalaze ozonske rupe. Konačno, probat ćemo implementirati komunikaciju u X pojasu, to vam je između 8 i 12 GHz. To u malom CubeSatu do sada nitko nije napravio. I ono što bih vam htio reći, a bitno je da izrada satelita je studentski projekt. Ovdje vidite sliku naše dečki iz tima kako pokušavaju dobiti signal sa jednog od CubeSata koji već putuju oko nas. Kao što sam rekao, treba nešto znati o solarnoj energiji, kontrola orijentacije, to se zove attitude control, kontrola podataka, komunikacijska elektronika, prikupljanje podataka sa senzorima, obrada slike i zvuka možda ako hoćete. I konačno, ova izrada satelita je studentski projekt, svi se možete uključiti. Mi također imamo otvoren natječaj za postdoktoranta na 4 godine, financiran od strane HRZZ-a. Imamo komercijalne partnere, Croatel i Geolux u ovom trenutku. I također postoji novi izborni kolegij u 6. semestru koji se zove Uvod u aerosvemirske tehnologije, pa možete doći to slušati. Ja bih sad tu stao, u stvari pokazat ću vam samo jedan slajd koji ću kasnije ponoviti. Jer ova 2 slajda sam vam htio pokazati na kraju prezentacije i pokazat ću ih opet. Naš tim, vidite ovdje društvo, se sastaje svakog petka u 3 popodne gore na Zavodu za radiokomunikacije. Ako vas zanima, dođite, pa ćemo se organizirati, ko će šta radi, šta vas zanima. Hvala. Now we're going to continue in English, and I'm going to invite Professor Kamps to give his presentation. Yeah, we don't have that much time. I'm late. Yeah, here. Malo sam pridružio. Aha, ovdje trebam stisnuti. Thanks. Here you go. So just hold this 5 minutes. Can you just hold this?
Presentation? Yeah, I will use mine. I see. Working. Yeah. Okay, good. Wow. Good morning, everyone. My name is Adriano Camps, and I'm a professor at the Technical University of Catalonia in Barcelona, Spain. I work in the School of Telecommunications Engineering. My work is, I work in remote sensing, okay? And just before I start, and this is something I always have to say, why we do CubeSats, okay, in the School of Telecommunications Engineering? Well, the reason is quite simple. It's more than 80% of what is inside has to do with ICTs, okay? So I always got complaints from the schools, from aeronautics, okay, because they wanted to have that on their own, but they didn't start it first. So we did, and for me, CubeSats, okay, are a way to test new remote sensors, okay? Other things that you once or twice in your lifetime will have the chance to put in a real ESA mission, okay? And to try new technologies. And this is the purpose. Everyone in the CubeSat world may have his or her interest, okay? But in our lab, particularly, it's for remote sensing and to test new technologies. And what I'm going to try to talk, okay, in this challenging presentation, when Professor Dubravko asked me, he wanted me to talk about 3 different topics: the ADCS, the attitude determination and control system, the thermal and the power budgets. And that was a bit. So I have 75 slides in 1 hour. This is against all the standards that I tell my students to do, okay? I will have to go a little bit fast, but you will have the slides with, I hope, information that you can use afterwards. So if I'm rushing or passing some slides fast, it's not because I don't want to explain, it's because of the time constraints. Okay, I could be talking for 4 hours and still I will have, will be leaving many things in the I want to thank some of my students. I just listed here 3 of them, okay, but actually this is a teamwork. Okay, you have seen the picture of your team. This project, and this is one of the things that you have to learn. This type of projects lasts many years. When I say many, in some cases, like in KubeCAD 1, it lasts more than 10 years. Okay, for many reasons. Okay, including problems with the lens, which means basically that the team will renovate over time. Okay, so in KubeCAD 1 we have involved more than 120 students. That's a lot. Okay, and in KubeCAD 4 that I will be talking more than 30 students already. Okay, so without more delay, basically my talk today will be about an introduction of this mission, KubeCAD 4. Okay, and then I will focus on the 3 topics I was asked to talk about: the attitude determination and control system, from now on ADCS, the thermal control system and the thermal design. So things, basically, I will focus on things that you have to take care of or be aware of before starting your own mission. Okay, and then the last part will be the electrical power supply, from now on EPS, and how to dimension the power system. So the KubeCAD 4 mission. We call our series of CubeSats, instead of CubeSats, KubeCAD from Catalonia. Okay, so we play with the name, and so far we have been involved in 5 CubeSat missions. KubeCAD 1, the first one in the series, was actually launched earlier this year, 2 weeks ago. Okay, November 29th, using an Indian launcher, PSLV. You can type in the internet. C43 was the name of the launch. KubeCAD 2 was launched in 2016, August 2016. KubeCAD 1 included 7 small payloads and technology demonstrators. It's one unit CubeSat, so a cube of 10 centimeters side. KubeCAD 2 was a 6-unit CubeSat, so basically the size roughly of a piece of paper, like this, okay, and this thick. Okay, and it included a novel type of payload that I will be talking about later because it's repeated, which is a GNSSR. It's basically a B-static radar using signals of opportunity from navigation satellites. KubeCAD 3 is on hold because of some budgetary restrictions. That was actually driven by the Cartographic Institute in Catalonia. Okay, and then the 2 missions that we are working on right now are KubeCAD 4, okay, and FSSCAD, which is composed of 2 KubeCAD 5s, A and B. Okay, what do we do? Basically, we integrate all these activities in the curricula of Telecom Barcelona. We do have a lab where we have a clean room with a thermal vacuum chamber, a shake table. We also have some Helmholtz coils for attitude determination algorithm testing, and we do have a ground station in Montsec, close to the Pyrenees. Our first one was in Barcelona. When we built it in 2007, the RFI environment was much cleaner than it is now or 2 years ago. Okay, so we have basically to move the ground station as far as we could. Okay, so KubeCAD 4. Well, the idea of KubeCAD 4, if you want to summarize in one sentence, is to demonstrate the capabilities of nanosatellites, okay, for challenging Earth observation using GNSSR. GNSSR stands for Global Navigation Satellite System Reflectometry, okay, and also L1 microwave radiometry, as well as for automatic identification system. So we have 3 objectives: a miniature GNSSR receiver that is actually being implemented using a software-defined radio, as small as this, as the one that you can put in a pen drive for your computers to watch TV. Okay, it's actually the same one, the same chip, okay, with the same chip but tuned into the band that goes from 1.4 to 1.427. We will be, not the whole band at the time, okay, but by slices, we will be operating it as a microwave radiometer, basically to detect sources of RFI. So here you have two examples. This is a map for salinity and ocean and soil moisture from SMOS, a mission working at Elban, and this is the map of RFI. So there are regions in the world where RFI is constantly there, usually linked to wars, okay, because military basically tend to jam all the spectrum, but also in other regions like in China where the enforcement of spectrum regulations are not, let's say, very tough, and the spectrum is totally corrupted, okay. This slide tries to show also the concept of GNSSR. So you get the navigation signals that you use basically to navigate, but you pick the direct and you get the reflected, and in the reflection process you get information on the surface where the signals are being scattered. And the IS receiver is basically a beacon that is transmitted by large ships basically to provide the information. Okay, so we will be using an helix antenna for these two and basically a monopole for that one. Okay, so this is our CubeSat. Okay, so this is a render. It's a 1 unit CubeSat. The dimensions are roughly 10 centimeters. Okay, a little bit longer in the z-axis because of these tips over here, which basically separate one CubeSat from the next one when they are in the pod. Otherwise, they will crash. Okay, weight is about 1 kilo. Okay, on the different subsystems, and as I think it has been explained before from my zero knowledge on Croatian, okay, you have the onboard computer, okay, you have the electrical power system, you have communications, okay, which we are using is the radio amateur band from 433 to 438 megahertz. And we have, in this particular case, an attitude determination and control system, because in this one, we need to point our long antenna to the nadir with some level of accuracy. Okay, so this is probably a constant in many satellite missions, is that you have a mix of subsystems from different manufacturers. For example, we use the onboard computer from Gomez Space. Actually, this one is no longer in the market. They have issued a new one. And this one is the power supply. Okay, from antenna we use the easiest one. Okay, it works pretty well. So actually I have to say that we are using these ones because these were the leftovers from the engineering model from CubeCat 2. So in your university you need to reuse things as much as you can. So if I had other budget, probably I would have made another decision, but in this particular case, we use what we already had in-house. We tested, it keeps working, so no problem. Okay, the rest of the subsystems, payloads, attitude determination, and control system, etc., it's made in-house. Okay, so we have full control on what we did, and we know basically weaknesses and strengths. And of course, we do the payload. This is the slice of the satellite, okay, with the deployable antenna. It's an antenna that when it is deployed, it's 55 centimeters long, so it's not bad. Actually, it provides the same directivity as the 6U CubeSat in CubeCat 2. Okay, but this way we do not need such a large CubeSat, which is far more expensive and also far more expensive to launch. Okay, we do have the magnetorquers, basically 2 coils, plus another one, this one here, which is this coil wrapped in this direction. We have an interface board that connects several boards, but also to the outside, because your satellite will need some umbilical cords, and you will need, when it's closed, okay, you cannot access it. You need to access to it, reprogram the computer, check that everything is working, and so on. The EPS, the electrical power supply system, the onboard computer, the communications board, and the deployment system for the UHF, VHF antennas. This is from the other side, so you can get a little bit more the perspective. You see the batteries now that were on the other side, okay, of the EPS. And here is the satellite in the stow configuration and in deploy configuration. Okay, so once it is deployed, okay, this helix antenna, that is the one that is providing us the basically the receiving element for both the radiometer and the GNSS reflectometer. This is the antenna that has to be looking to the nadir direction, okay, of course, the beam width is something like this, so you do not need a 1 degree pointing accuracy. Actually, our requirement is on the order of 10 degrees, so we are still within the antenna beam width. Excuse me. And, but still, we need to be pointing to the nadir direction. From the electromagnetic point of view, this antenna has to be a left-hand circularly polarized antenna, which means that it will pick the GNSS signals that come from the satellites are right-hand, okay? But after reflection, they become mostly left-hand. Basically, I don't know if you are aware, this is how the electric field turns, okay, as it propagates. So I see some people saying yes, it means that you are following this type of courses, but sometimes you don't know which is the audience. So that's why from time to time I give these extra details. Okay, so things that you have to take into account in your mission. So it's not just turning it on and it works, okay? In the same way when you boot a computer, okay, at the beginning it does something, okay? Sometimes you see this black screen, sometimes some letters, okay? Okay, in a satellite mission there are also some steps, okay, until you can start using it, okay? So the very first thing is that you need to connect it, okay? And over here, okay, you see this? This is a switch. Actually, depending on the launcher, you may have more than one, okay? And actually for the Flyer satellite in QCAT-4, we are required to put 3 switches. So 2 of them are in these sticks, and there is another one for which we have had to manufacture one of these rails because it's in the middle. Okay? This is ESA that is crazy about security, about redundancy, about these sort of things. Okay? Most of my American colleagues with 1 switch, they do it. Okay? But ESA has asked for 3 switches in series. So when the satellites get deployed, one from the other one, okay, it's when these switches get connected. And at that time, it's when, let's say, your computer boots or it starts booting. But it doesn't mean that the system will start working, okay? What it means is that this is the beginning of your timer, because you cannot start transmitting or doing anything for a period that lasts between 30 to 45 minutes, depending on the launcher, okay? So this is what you do at the beginning. After that, you do your antenna deployment, and usually your satellites start, I mean, they are not injected and they are not still. They just move. I don't know if you have seen the satellites from Planet when they are injected in orbit, they start spinning like crazy. So the first thing that you need to do is to detumble them, to slow down so the angular speed is smaller than a given threshold. Okay, so you can, the attitude control system can take control of it. Okay, then when the LEOP, the launch and early orbit phase ends, okay, well, sorry, I missed the commissioning part, okay, which is basically the health check of all the different subsystems, deploy the antennas if needed for the payload, and pointing to nadir. Okay, you finish the launch and early orbit phase, and then you enter into operational phase, which in our case it consists of 3 modes. This is the nominal mode, which is basically what you are supposed to be doing most of the time, okay? But from time to time things happen, and these sort of things that happen are that you may have a critical event, something may go wrong, okay? So you enter into survival mode. So it's don't do anything, just try to keep alive, okay? And then the typical transition is actually from nominal to sun-safe. Okay, depending on the battery. The amount of power that you can generate is usually quite limited, so when you transmit, typically, you spend a lot more power than you are able to generate, so basically you are draining your batteries, and if you drain your batteries, at some point the charge will be too low, and as with your cell phone, you will have to recharge it from time to time, so you enter into a sun-safe mode in which basically we just recharge batteries until they are almost fully charged. Okay, when this basically the whole history of the satellite runs jumping between one state and the other, hopefully not that much in the survival mode, okay, between these two. And at some point in time, the satellite life will come to an end, okay? And when people ask you, how long will your mission last? Well, I always have 3 answers. Well, you can say when it will re-enter, and that will depend basically on the height, in the orbital height. Atmospheric drag basically slows down the satellite, and then the height starts decreasing, and then the satellite re-enters and gets burned in the upper layers of the atmosphere, around 70 kilometers. Okay, that's one. The other thing is that because it receives so many high energy particles, okay, the electronics get damaged, and at some point they no longer work, okay? So that's another way of dying, of passing away, okay? And another way, and it's likely to be the one that will happen in most of the satellites, is because the batteries pass away, okay? I will comment that in the latest part of my presentation, but basically, if you treat well your cell phone, you need to change your batteries about once every 2 years, okay? And I say if you treat well your cell phone, because if you do not, basically you discharge the batteries a lot, your batteries last less, okay? So think that this cycle, during the day you talk, during the night you recharge your phone, which is basically what you do, leads to 2 years, which is about 720 cycles, or 30, okay? And actually this is the number of cycles that you can charge and discharge a lithium-ion battery. Okay? However, if you are in orbit and you do that 14 times per day, which is the number of orbits, you can divide these 2 years into 14, and this will give you how long your batteries will last. Okay? Less than 2 months. And you don't want this to happen because you are not working for many years for a mission to last 2 months. Okay? So what do you have to do? Treat your batteries well, or put extra batteries so they do not discharge that much. Okay? And this will be part of the engineering design process on dimensioning the power system and the batteries. Okay? So this is it. Okay? So not going into much details for the different modes, this is the different payloads, the different subsystems that are turned on, off, and to which level of duty cycle. For example, even in survival mode, you cannot turn off the OBC. Okay? Even at a low frequency, even with very minimum power consumption, you need your computer to be awake, otherwise, I mean, it's totally dead. Okay? Of course, you need your EPS. Okay? How are you going to charge your batteries? How are you going to feed your computer? Okay? In our case, we also need to be pointing to the nadir, but this one is a little bit tricky because we have magnet torquers, so coils, but we also have a gradient. The antenna is also acting as a gravity gradient, okay, a boom, to align the satellite in the direction of the gravity field of the Earth, okay? And then we also have, well, this other subsystem, but the beacon, and I don't see where is the beacon, this one, okay? This is the beacon. In survival is 10, sunsafe is 5, okay, usually it's at 10. I think actually these two are exchanged. This one should be survival and this is sunsafe, okay? Because in sunsafe, in survival, you transmit a beacon even just from time to time to say, hey, I'm alive. So this is very important, okay, for the last part of this presentation, the power budget. Okay? Other things that you have to worry about the end of the life, bad, because it can be hit by some particles, so there are some requirements, okay, or you can estimate, which is the, excuse me, the number of impacts that your satellite may receive, because there are some debris, because there are some particles up there, so depending on the height you will be receiving, this is the probability, okay, impact rate in number per year, depending on the diameter, okay, and depending on the height, okay, and what has happened? Okay, also the re-entry, okay, if, as it was originally said, we are going to be launched from the International Space Station, okay, orbital height is about 400 kilometers. Basically, this means that depending on the section, the cross-section, okay, this and this, the lifetime will be between 8 months and 14 months. Okay? These small cubes that doesn't have any type of propulsion mechanism to raise the orbit, so it will basically be falling down, and depending on the orientation, so the small one is this one, when one side is facing, one face is perpendicular to the velocity vector, this is the smallest cross section, the largest is when actually it's almost in one of the vertex, okay? Then it changes between 8 or 14 months, okay? So, in summary for this one, okay, you need to design your mission to last for 14 months, no more than that. So, when thinking about the batteries, etc., or the effect of radiation, etc., think about this as the maximum time span of your mission, okay? So, now, going into the details, attitude determination and control system. In our problem, okay, the satellite cannot be in any random orientation. In some other missions you can, and actually most CubeSats do not have any type of attitude control system. But in our case, we need to have the z-axis pointing to the nadir direction, because we have this long antenna, okay, that has to be facing towards the surface of the Earth. So the ADCS process includes the following, let's say, sub-process. One is basically to determine your attitude. The attitude is your relative orientation with respect to the Earth, okay? You need to implement a control algorithm, and then you need to actuate, okay? So actually it's a closed system in which you determine how you are oriented, okay? You have some rules, and then you actuate, okay, to enforce the attitude that you are looking for, okay? So the different modes that we have implemented in CubeCat 4 are the detumbling. As for any other satellite, as it is ejected, it has these arbitrary rotations that you need to slow down, okay, until it can, they can get control. Then we have nadir pointing without gravity boom, okay, so this is the gravity boom. And then we have nadir pointing once the payload antenna is deployed with the gravity boom. So basically the equations are the same, but basically what goes into the equations is different, okay? Because the matrix of inertia is different when the satellite is in a stow configuration or deployed configuration. So, sensors, okay? I'm not going to enter into the detail, but that may be helpful for your CubeSat mission. For the design, these are the gyroscopes that we are using, magnetometers and sun sensors, okay? So, we have this one, okay, that provides a measurement of the angular speed of the satellite. With the magnetometer, we measure, I mean, it's the same like in a cell phone, okay? How the cell phone knows the inclination is just by comparing, okay, with the magnetic field of the Earth, okay? In a cell phone, you also have accelerometers, okay? But in orbit, because the centrifugal force is compensating the other one, you cannot rely on accelerometers. Actually, the reading will be 0, okay? So if you have an IMU, inertial measurement unit, say 9 degrees of freedom, forget about the 3 accelerometers because they cannot work, okay? You only can rely on the 3 gyroscopes, the 3 magnetometers, and then of course the magnetometers have to be used in conjunction, okay, with your knowledge of the magnetic field of the Earth in that particular position. So other things that you have to do is to propagate your orbit, get an estimation of where you are, compute the magnetic field of the Earth in that position, look to the magnetometer readings, compare both of them, and from that you know basically how you are oriented, okay? So the process is a little bit more complicated, okay? And then we have sun sensors, okay? Basically these are photodiodes, okay, that tell you in which direction the sun is illuminating. And we do have 5 and not 6, basically because in one of the sides we do have the antenna, the deployable antenna. So we cannot put another diode over there. Okay, and as actuators, we have 3 coils. A coil is basically an electromagnet. So as you circulate current, the more current you circulate, the stronger the momentum will be. Okay? You can also reverse the sense of the current. You can play with the current that circulates in the 3 orthogonal coils. Okay? And this way you can create any arbitrary magnetic field that will tend to align with the magnetic field of the Earth as a compass. When you have a compass, it tends to align with the magnetic field of the Earth and point to the north. Actually, they are flat, okay? But if you had a 3D compass, it will point basically in the northern hemisphere like this, okay? In Barcelona, it's about 78 degrees or something like that. So it's they are not as they draw it in the physics books, okay? That like going up from the north poles and entering the south. Actually, they are much more inclined. But this is used, okay, to actuate, okay, and point the satellite into the desired direction. So the main goal of the tumbling, which is the first thing that the satellite has to do, is to reduce the initial angular speed of the spacecraft to a value, and this value is TBD. It will depend on you, okay? But usually, in our case, is around 2 degrees per second. We do not reduce that much low because then the gyroscope's noise is on the order of half a degree, 1 degree, depends on the sensor that you are using. Okay, so you cannot reduce that arbitrarily because then you will be measuring the noise. Okay, this mode has to be autonomous, it has to be robust, and even in some cases without the need of the onboard computer, depending on how reliable you want things to be. Usually you put the computer in the loop, but it can even be implemented without it. And the tumbling algorithm is actually very simple because you take a measurement of the magnetic field, okay, and then you multiply by a proportionality constant, you reverse the sign, and this is the torque that you are applying. End of the story, okay? Okay, one of the things, and you will start seeing from time to time that I put some tables like this, is that you need from the very beginning, and this is very annoying, especially for us, but for students as well, okay? You need to define requirements, okay? Requirements for everything, for the attitude determination, for the communications, for the thermal control, for everything, okay? Because these requirements that are top-level requirements, okay, you have the mission requirements document, top level, that you translate into system requirement documents at subsystem level, and that will basically we use as guidelines for the design. So your design will have to be compliant with those requirements, which means that if you comply, the mission will work. If it is not, it will not work, or it will not work as expected. Okay? But you need these requirements in order to establish some sort of traceability, okay, from the generic requirements, the mission at mission level, okay, down to the smallest subsystem. So our requirements are, okay, that it has to be able to tumble to stabilize the satellite attitude, and from an initial speed of 30 degrees per second down to 2 degrees per second after 24 hours. So basically what we have is a loop. It changes, so change is negligible. Basically this is the reading from the gyroscope. Okay, if it is small, then I'm down. Okay, but if it is not, keep applying the tumbling algorithm. But when it is down, okay, the satellite is detumbling, then you can start doing something else. And just a couple of examples of the tumbling when it is in a stowed configuration. Okay, after about 10 minutes or so, 600 seconds, okay, we managed to detumble it. Okay, in CubeCat 1, by the way, we have hysteresis rods, okay, not coils. So the process takes a lot longer, but this one is a totally passive system. So I mean, the risk of failure is almost zero, unless during the launch something has broken. Okay, and in deployed configuration, the system takes a little bit longer, well, significantly longer actually. Why? Because then you have this long antenna, okay, that is actually working as a boom. So if it is spinning, it actually takes a lot longer to slow down because the magnetorquers, these coils, are the same, so they cannot apply a stronger torque to slow down the system. Okay, and also it also has some flexibility, so it's a big mess to model. But in the end, the system is capable to control the angular speed to within a couple of degrees. Okay, so for the nadir control part, we have the detumbling, which is basically the derivative. You take the angular rate, the measure, the reference, and then you apply a constant, a proportionality constant. And for the attitude control part, basically it's a proportionality constant that has to be multiplied to the attitude error. Okay? And this is the torque that you have to apply, and the idea is that the minus c-axis, okay, has to be pointing to the nadir direction with an accuracy, again, that will depend on your system requirement document, an accuracy of 10 degrees, which is a fraction of the antenna beam width. Okay, so more requirements, and we will not enter into the details. Some of them I have already mentioned. So the approach that we follow in CubeCat 4 is a fully magnetic attitude control. So we have 3 magnet torquers in the 3 orthogonal axes, plus gravity gradient control. Okay, our own antenna helps us a boom, okay, to stabilize the attitude of the satellite. And here a couple of more examples, okay, with the Euler angles, okay, everything is stable except the yaw. So when it is pointing down, okay, with magnetic control, you lose the control in one of the axes, so actually it can rotate, but we don't care because the antenna beam is already pointing into the nadir direction. Here you see the quaternions that are already stable and the angular speeds that are stable for the 3 of them. Okay, this is the part that I know the least because this is where the aeronautic engineers came into the business. Okay, how to determine from the readings of the magnetometers from the sun sensors, etc., determine the attitude that has to be input. Frankly, this is the part that I master the least. Okay, so these slides were passed to me by one of the members of our team. Okay, and he's an master's in aeronautics. Actually, he's engineer in aeronautics and master in aerospace. Okay, and the algorithm that is used is the optimal request. Here are some slides explaining. I have some additional material, but this is not my field, so I will not enter into some dangerous sense. Okay, and basically the thing is that at the end of the day, it works, and the quaternions are properly estimated within the required accuracy. Okay, so this part we are on the safe side. Other sources that in our particular case are not negligible, okay? Sources that distort, which are basically which other things can be creating an extra torque that will change the attitude of the satellite. Okay, we have the gravity gradient. Actually, we are playing with it to align our satellite. We have also the aerodynamic disturbance, which is basically the friction, okay, of the atmosphere. Even the atmosphere is very, very thin, the density is very, very low, okay. This is what forces the satellite to re-enter, but imagine a satellite that is a box like this, okay, and the cylinder is more or less this size, but like this. And it has a mesh, okay, a material that basically gives some rigidity, otherwise it will be like a spring, okay, moving without control. Can you imagine that the atmospheric drag on this side of the antenna, it's quite strong. So basically, if we don't do anything, if we do not actuate, the satellite, I'm glad I'm checked, the satellite will turn like this. Okay, just because of the drag, because it's much higher in this part than in the box of the satellite will be orbiting this way. So the antenna, if we do not actuate, will not be pointing at all into the nadir direction. Okay? We also have the solar radiation pressure. Okay? These are the photons that are impinging into the surface of the satellite. And also something not to be neglected is the magnetic residual moment generated by the currents that are circulating into the satellite. Okay? And this for example, in our case, if you look to the relative weight for our orbit, okay, that's a STOW, but in deploy configuration, you see that the two more important ones are the atmospheric drag and the magnetic residual. So we need to take that into account. So these are things not to forget. And by the way, in CubeCAD 2, we found an error in the solar panels that we purchased. Okay, the routing, okay, from the solar cells into the satellite was creating a huge loop that was creating a torque larger than the one from the magnetorquers. Okay, so things to be taken into account during your design. Okay, we solved that. Okay, but I'm glad that 2 months before launch we realized. Okay, well, before launch, no, before integration. Okay, so the motherboard that we have implemented, because this is ours, includes the gyroscopes, magnetometers, photodiodes, okay, for the sun sensors, magnetorquers, and then all the control unit. Okay, so this is how it looks like. We also added some wireless communications capabilities in order to avoid plugging in cables, etc. That for debugging was a little bit messy. And what is important, well, these are the drivers, so basically H bridges for all the currents. Okay, I didn't say, but instead of changing the current, we apply a constant current and we duty cycle the current. We use a PWM. Okay, that's basically another way of changing the average current. And we have an H bridge in order to be able to reverse the sense of the current. Okay, and as a sensor, the microcontroller, and I think it's in one of the next slides. Okay, is this one? Okay, it's an STM that I strongly recommend you to use because the power consumption is very reduced and it's very reliable. It has been tested a number of times in space, so it's okay. Okay, so things that you have to worry about that is the sensor characterization, the linearity, especially for the photodiodes. Okay, resolution and noise for your ADCs. Also for the PWMs when you actuate. Okay, for example, in one of our satellite missions, the PWM, the drivers that we got because we purchased, work with a resolution of 1%. And when we were doing the analysis, the simulations with 1%, okay, so this is the minimum step you can change your current. That was way too large. I mean, way too large. I mean, bam, changing by 1% changed the attitude too much beyond specs. Okay, so basically we had to do our own drivers in order to be able to go down to 0.1%. Okay, so this is the sort of things that, again, you see that we have a mix of things that you purchase, things that you develop yourself. You tend to think that when you purchase something, it's going to work because you have paid for it. It's not necessarily the case. Let's say this way. Okay, you have to integrate things. We have, I mean, just another anecdote. We have purchased some things from 2 manufacturers. Okay, and we have realized that okay, we tested, it worked. We tested, it worked. When we put together, it didn't work. So, what's going on? What was going on is that they use a function with the same name. Okay? So when the compiler went through it, I don't know for which reason, sometimes it compiled one of the functions first and then the other, so one thing started working crazy or not working at all, or the other way around. This took us 3 months of debugging. Okay, so take things like that into account in the schedule of your project, because then you're in trouble. Okay, so not necessarily because you purchase it's going to work. Okay, there are many, many hidden surprises on the way. Okay, check temperature drifts. For example, checking FSS-CAT, one of the payloads, we realized that above 55 degrees, one of the subsystems stopped working. Okay, so check all these things. Of course, you will need to do vacuum tests. Okay, especially if you are using commercial off-the-shelf components with not ceramic, so plastic housing. Thank you. Okay, and then for the magnetometers, again, linearity, resolution, the 1% thing that I was saying, and temperature drifts as well. Okay, well, for the thing, check the algorithms. One of the typical errors that happens is that you put your constant wrong for the detumbling algorithm. Okay, you need to check it. How? In an air bearing with handheld coils. Okay, if the sign is wrong or you mounted the coil the wrong way, instead of slowing down, it will accelerate. You need to check that. Okay, there was an example with the Swiss cube that happened. And then the only way was, okay, draw completely the battery, okay, and then basically upload a patch, a software patch, okay, with the sign change, okay. But that was, I think this is one of these well-known examples of lessons learned from others that you have to apply to yourself in order not to make the same errors. Okay. So I already mentioned about the STM, like the single board, okay, the computer that controls all the ADCS part. Okay, and here you have a little bit of the flow diagram of the different tasks. I will not enter into the details, okay, but basically this is for the detumbling, for the nadir, and then how all the check-ins and all the telecommands and housekeeping data is sent. My recommendation, and we put that information into the beacon. So the beacon is not just, hello, I'm here, and this is my identifier. Okay, try to put as much information as you can batteries, voltage, state of charge, the temperatures, speed of rate, whatever you have in the beacon, because this will be very useful information to debug the system. And also the beacons, because they will be received by anyone in the world, all the radio amateur community, you will have much access to all this data. Okay, these are the different processes. I will stop. Let me enter into the thermal control system. 25 minutes left? Okay. Well, when you are when you have a laptop, okay, basically the most important mechanism that you have, okay, is the fan to keep the temperature under control. Well, this is not the only mechanism, this is what you listen, but also in the laptops, because they are very thin, you have the CPU on one side, and then you have the fan and the system that evacuates the heat on the other side, close to one of the edges, okay, because you need the air to get out. Well, in that particular case, in most of the laptops, you have something that is called it's a copper thing, you see it, it's like a snake, okay, this is called a heat pipe. Okay, that is widely used in space, okay, to transfer heat from one place to the other. Why? Because you don't have convection. You cannot put fans, you cannot do most of the things that you do here on ground, okay, to keep the temperature under control. The only two mechanisms that you have are conduction and radiation. Okay, conduction works well, even though I will comment later, it's very difficult to model. But when you have the satellite on the sun is hitting on one side, the temperature can get really hot, and the side that is looking to the deep space can get really cold. I may be talking about plus 80 or more and minus 30 or less. Okay? And all this gradient in less than 10 centimeters. Okay? So you need a way basically to try to balance the energy as much as you can, if after your analysis you have to. And the other mechanism, of course, is radiation that will depend on the properties, basically, which are the materials that cover the surface of the material. Because you can have the same material but paint it with a different one. So basically the materials of the painter, or the golden, or the silver, or whatever material you are using to cover them. Okay? So conduction, okay, it's proportional, okay, to the gradient of temperature. The larger the gradient, okay, and depending on the material, some materials are more insulating, others are more conductive, so the value of K will change. And radiation basically follows the Stefan-Boltzmann law that says that the amount of energy that is being radiated is proportional to the absolute temperature, to the fourth power. Okay, it's also proportional to this constant, which is the Stefan-Boltzmann constant, to the area, and to a parameter that is critical, which is the emissivity. Okay, and that's why you see the satellites sometimes like wrap in a golden type of foil. Okay, it's not because they are very expensive. They are very expensive, but it is not because of this golden paper. Actually, this is to keep the temperature as warm as possible inside. So when we are in a space, we have different sources of power coming in and out. Of course, the most important one is the sun. We have the direct radiation, but we also have the Earth albedo, okay, which is basically the reflection from the sun reflecting on the surface of the Earth and then reaching the satellite. We have the radiation from the Earth, but because the temperature of the Earth is around 300 Kelvin as opposed to the 6,000 Kelvin, which is the physical temperature of the surface of the outer layers of the sun, instead of in the visible near infrared part of the spectrum, most of this radiation occurs in the thermal infrared, around 10 microns. Okay? And also we have the CubeSat itself, the satellite, that is radiating to the outside. And internally we also have power that is being dissipated. We have all the electronic circuits that are dissipating energy. Okay? So the equation that basically governs all this is the rate of change of the temperature, okay, depends on, assuming everything is, this is the isothermal approximation, that everything is the same material, uniform, everything, the simplest possible model. Okay, so this is the density, this is the specific heat capacity, this is the gradient of temperature, and this is the in all the sources of heat that are coming in, so direct, reflected, and infrared, okay, from the Earth, the out, which is basically what is being radiated, and the heat that is generated internally. Okay? So, again, you have some requirements, okay? And I will not go into all these because I can explain it better with a plot and then with a table, and you will understand it better. But again, you need to define clearly which your requirements are. So, you are going to do your simulations, and as you will see, these are very, very tricky. Depending on the modeling, you will get one result, you will get another one. So typically, you make your design, okay? Depending on the model, even if they are commercial softwares. I mean it's not your software that is of poorer quality than the commercial one. No, not necessarily, okay? You get different results. Why? Because the approximations, numerical approximations, or whatever that are inside. So you have already some uncertainties, okay? So put a margin, plus minus 10 degrees. On top of what you get, put plus minus 10 degrees, okay? And on top of that, for the acceptance, put another plus minus 5, and for the qualification, another plus minus 5 degrees. Okay, these are typical values. So you make your simulations, and on the end, you end up with plus 10, plus 5, plus 5, and minus 10, minus 5, minus 5. And this is the way to be on the safe side. Sometimes this is a bit exaggerated, but this is life. Okay? So, and you will understand very easily. When you get a data sheet from some products, electronic circuits or whatever, they give you the temperature range in storage and in operating conditions. Okay? So you go through all your subsystems, tac, 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 you go through all this. Looks like this is a comprehensive list. No, it is not. Actually, each of these subsystems, you can go for all the individual chips that go into the onboard computer or into the EPS, etc. But this result, what I'm going to tell you, it's quite general. The batteries are the ones that have the most stringent temperature constraints. Okay, typical values, maybe a little bit negative, and 40, 45 Celsius positive. Okay, from all. So you need to guarantee that the batteries are not going to get neither too cold, neither too warm. And of course, basically this is the variation, the different, you simulate it, and then you put all the ranges. For the predicted plus minus 10, just to be on the safe side, and then for acceptance and qualification, plus 5, minus 5, minus 5. So, which mechanisms do you have for the thermal control? You have passive means and active means. So passive is basically thermal insulation, coating, okay, ways nothing that generates heat artificially. So it's basically to either isolate or to conduct better the heat, okay? Or the active is basically heaters, okay? Or other mechanisms that change the physical properties, for example, louvers that, but these are seldom used in CubeSats, that modify the outer color of the satellite, okay? I have seen them in larger satellites, but not in CubeSats. Okay, so the design process that we follow, because it is quite complex and you need to take some design decisions early in the beginning of the mission, we do the isothermal analysis first, okay? This is very simple, but it will give you already an orientation on where you have to go, okay? Basically from what you have to die from. Okay, and then you do the radiation-only analysis and then the full thermal model. For this one, I gave you this tool during the Young Professionals in Space and also in the pen drive, okay, that you can use, which is a MATLAB tool that implements this, some of the functions in this MATLAB toolbox. It's not too expensive, so I strongly recommend that you get it. And for these ones, you will need more sophisticated software, but in the end, you are going to need it anyway. You need to identify basically which are your hot and cold worst cases, depending on the orientation, in the orbit orientation, which is basically the beta angle, okay, which subsystems are turned on or off, etc. So in all the different configurations, this was our worst hot case, and these were our worst cold cases, okay? And your system has to withstand, okay, in these two extreme cases. So the first model is the isothermal, okay? We have different properties for the different coatings, black paint, gold, tin. This FR4 is the fiber that is used typically for printed circuit boards. Okay, absorptivity, excuse me, is in the visible near-infrared part of the spectrum, emissivity is in the thermal infrared. That's why the same material has different properties. At the same wavelength, these two numbers will be the same. And what matters is this ratio, because it tells you how well it absorbs or emits. Okay, the black, it's very close to 1. Okay, ideally, if it is a black body, it will be 1. But the gold, as you see, absorbs more than it emits. That's why it keeps the temperature warm, okay? So basically you run the isothermal analysis with MATLAB. You cannot see it here, but I mean, you can get the slides afterwards, okay? But it is on the safe side, but it already gives you some indication on what type of coating you are going to need, okay? Because instead of coat, you put more solar panels or you put another material, you will see immediately, for example, that the average temperature goes well below. And when I say well below, it may be 260 or 250 Kelvin. Okay, and that's way too low because you will need to put your heater on all the time, and that will have implications in the power budget that I will briefly explain later. Okay, so you do all the modeling, okay, incrementally, so get it complicated little by little, and you see all the evolution of the temperature for the inner layers, for the outer surfaces. You can get very detailed model of the whole structure, okay? Internal PCBs, the structure of the CubeSat, that's easy structure, okay? More things to worry about when doing this modeling is the interconnection between the different structures, okay? Because many models, or the way, this is not my part either, okay? But we have an industrial engineer that is doing that. If you do not model the contact properly, then the heat is not transferred from one to the other. Okay, so your modeling is totally out of reality. Okay, it's totally wrong. So these are things to worry about when doing the modeling. So this is just to show you the level of modeling for all the spacers, all the PCBs for the different ones, even if the layer, for example, the OBC or the EPS, okay, you get to know where it was. Okay, here, okay, this is the EPS, 6 layer, this is 4 layers, etc. Okay, why? Because something as simple as a ground plane, okay, in between a PCB may change your result completely, because the way the heat is transferred in the PCB through the FR4 or through the copper layer is totally different. So you have to go down to this level of detail if you want to at least try to do things right. Okay? More modeling, the batteries, important to sense which is the temperature that we are going to have in the batteries. Okay? We also model the antenna, okay, that has a Teflon fabric supporting it, okay, to give it some rigidity. Okay, and again, you run the simulations, you see that one of the sides, I think that was about 80 Celsius, but this one, if I remember properly, that was like 150 or 180 Kelvin. Okay, so you have huge temperature gradients in the whole structure. And of course, you need to guarantee that the metal, okay, that makes the antenna, it's going to withstand all these temperatures. It's not going to break, okay, etc. So these are the results. In the hot case, maximum temperature for the batteries, 2 degrees above the absolute maximum. Okay, the cold cases, okay, so you see many that are non-compliant. Okay, this is for the deploy configuration and the stored configuration on the right. And then if the heaters are on, now we are compliant. Basically, you put the heaters in the battery to raise the temperature, so it works. Okay, so this is just to show you. And this has an implication on the power budget, because then you need to run this analysis over the orbit, and you will compute how much time your heaters have to be on so that the temperature doesn't go under the critical value. Okay? And then it goes to your power budget, that is the last part of my presentation. Okay? So conclusions of the thermal analysis, which is also critical. Okay? Use initially simpler models to give you in the design. The batteries are typically by far the most critical element of all the different subsystems. Okay? Try to figure out which is the cold and the hot worst cases, and I'll target the analysis in these two. Okay? For the cold cases, you will need heaters. In our case, we need to turn on the heater about 30% of the time, which is not surprising because this is basically the fraction of the time the satellite is in eclipse. So as a rule of thumb, you can do like this in your very first stages of the mission analysis. Okay? And well, this is about a little bit of the same. Okay? Use all these thermal straps, thermal pads to increase the thermal conduction, play with the different coatings, golden. For example, if you want to do your PCB, you can also ask them to be golden. Okay? It's a little bit more expensive, but from the thermal point of view, and also it will not corrode, okay, with the atomic oxygen up there. Okay? And then quickly, in 7 minutes, the EPS and power budget. Okay? Important things to worry about. Okay? Number one, it's obvious, but someone has to written it. Okay? The EPS has to fit all these systems. The EPS will need to recharge the batteries, okay? And you need to, in general, have a positive power budget, okay, in order to recharge your batteries. If it is not positive, it means that it's like in your daily life, you spend more money than you earn, okay? You can live while you have money in your bank account, but at some point, there is no more money in the bank account. If you keep spending more than you earn, you go bankrupt, okay? And that will be the end of the mission, okay? So this is the same. You need to earn a little bit more than you spend, or if not, you will enter into sun-safe mode, which is basically you do not spend, you don't go to the cinema, you don't go to the restaurant, you don't do anything, you just go into sun-safe mode, okay, until you have saved enough charge that you store in your battery to start normal operations again, okay? The batteries have to be properly dimensioned to store more energy, so the system can operate into eclipse mode as well, okay? And, well, you will need to note a number of parameters, how much power is consumed by the different loads, by the different subsystems, and which is the duty cycle, the capacity of the battery. Actually, this is more than to know. If you purchase, it's to know. But if you have the chance, it will be up to you to design and oversize the batteries. Okay? Available power that is generated, of course, the time that it's in the sunlight and in eclipse. Okay? And the different subsystems efficiencies. You will see that even you have 90% efficiency in a charger, etc. When you multiply 3 of those, I mean, you have lost a lot of energy in your way. And always consider the worst case. So, I was not expecting such a wide, that's why I put some equations, because I was expecting it was going to be more like a student type of class, so sorry about that. I have 3 equations, but this is just to help you to dimension your system. Okay? At the end of life, and this is important, your system has to work after these 8 or 14 months. Okay? Not at T0 when it is launched, but at the end. And it has to work also under the worst conditions. Why? Because I have not talked, but when the solar cells get warm, the temperature increases, their efficiency decreases. So they are not producing as much electricity as they are here on ground, okay, at ambient temperature. And also, as time passes, they get more radiation, also the efficiency decreases. Okay? This is important for satellite missions that last many years, not that much for CubeSat missions that last 1 or 2 years. Okay? But here you have to take into account, and I will not explain all the equations, otherwise I will not finish. You need to know which is the power that is consumed, okay? The power that is consumed in eclipse, the time it is in eclipse, the time that is in under the sun side, and the different efficiencies, okay, of the battery charger, of the battery discharger, all the bus regulators and back or converter or boost converter or whatever, okay? And you need to take into account all this to dimension the power that has to be generated by the solar cells. Okay? This power will depend on the area that is exposed. So basically in CubeSats you don't have deployables. Some of them now start having deployables because the payloads are more power hungry. This is the cosine that takes into account the projection angle towards the surface of towards the direction of the sun. Okay? This is the solar cell conversion efficiency. Okay? Be careful because that depends on the temperature and the radiation. Okay? So bring the thermal analysis into the power analysis as well. And then you have other loss factors. This is the packaging efficiency. Okay? Pay attention to that because even you see, or it looks like the surface of the CubeSat is totally filled with solar cells. Actually not. In a 10 centimeters, you put 2 solar cells, and you have a packaging efficiency of 62%. So only 62% it's actually covered by solar cells. Okay, and this is the total area, okay, that is not totally filled by solar cells. Okay, so the solar panel orientation also affects fraction of the time that is under light and under shadow, incidence angle, number of panels, and also the type of orbit determines how much time it's in eclipse or not, and the incidence angle. Okay, and then important, that's the last equation for the sizing of the battery. Okay, why it's so important? Here you have different types of batteries. Okay, here you have the voltage, but this is irrelevant at this moment. The capacity, irrelevant at this moment. Temperature range, it's important. Okay, it's linked to the previous analysis. And this is very important. This is the number of charge-discharge cycles up for a 75%. d.o.o stands for depth of discharge. Okay, so coming back to the mobile phone, okay, that you have to change your batteries every 2 years, here is the answer. You have about, for lithium-ion batteries, you have about 700 cycles of charge and discharge. Okay? If you want, but of course, with this, if you do that 14 times per day, count how many days your mission will last. So in this particular case, your mission will not last even the re-entry. It will pass away much, much sooner. Can you do something? Yes, the answer is make your battery pack larger so that spending the same amount of power, okay, you do not discharge that much your batteries. Therefore, the number of cycles increases. And this has to be larger, okay, than your expected mission lifetime. And this is one of the most important messages I wanted to transmit today. Okay, the rest is okay, how many batteries, how many cells each battery, the voltage of this, the depth of discharge, the efficiency, and the other are parameters that you have computed previously. But this will determine basically how many batteries you will have to put. Because of course you can get 3.7 volts with 1 or with 4. Why to put 4? Basically to decrease the depth of discharge and increase, okay, the duration of the mission. The architecture that we have, okay, I'm coming to an end. Solar cells in X, Y, and C in both. Well, actually not in the -C because we have the antenna, the deployable antenna. MPPT, maximum peak power tracker, battery charger, battery pack, and then we have one that is an unregulated line that we do not use in our case, and we have lines at 5 and 3.3 volts. Okay, this is the one that we are using. It's from Gomez Space. Okay, actually it was the engineering model from CubeSat 2. However, since we are going to be launched from the International Space Station as it is now, we had to change the batteries, okay, and use ones that are compliant for the ISS. Why? Because one thing is the satellite, there is no human beings over there, but in the ISS there are. So the batteries, actually the testing cost us 5K, so be prepared to spend money. Okay, it's really painful. And by the way, ESA did not rely on our own testing. So it has to be certified by somebody else and say, okay, if we purchase from them, you will believe us? Yes, okay, we pay, problem solved. Okay, more information that you can use. These are the solar cells that we are using because the solar panels we do our own. Okay, and actually the circuitry is from CubeSat 1, not CubeSat 2. Okay, the management for the different systems, for the heater, the different, that's important. Each of the systems has a point of load, okay, and it has a watchdog. So if we detect that something is has entered into an idle state, clack, we reset, we force a hard reset, okay, and the whole satellite has a hard reset every 48 hours, so every 2 days. So if something goes wrong, clack, hard reset, and this is a circuit that is apart, it's not hanging from the onboard computer. Okay, I'm going to skip this. This is the power distribution system for the different subsystems that we have. Okay, I'm going to skip this one. The different power budgets, okay, from the different stages in the different modes, and the net result is that the power budget has to be always positive. And last advices or things. What you should consider in your design, including the heaters, okay, related to the thermal analysis. In this case, in our case, maximum depth of discharge, less than 4%. Why? Because we need the batteries to last long, very long in time, and we do not. So basically, this is translated into a low duty cycle of the payload. The payload is operated only 10% of the time. Okay? Despite all this, okay, the mission is expected to last half a year. Okay, so it will pass away not because of the re-entry, but because of the batteries. Be careful also so that your system can withstand the peak currents that it will need, especially when deploying the antennas that you need to burn, and then you can have peaks that are important, okay, in some of the buses. At the beginning, especially, okay, and well, this is it, about 8 months at maximum, and well, you need to adjust all this, okay, for your re-entry. If you had, of course, attitude, some mechanism, propulsion mechanism to raise the orbit, your mission could last longer, and basically all this analysis for the power will be different. Thanks for your attention.
really intense. Thank you.
You have questions? Or you want to do it afterwards?
We're going to do afterwards.
Okay.
In the interest of time, we're going to leave questions after the next presentation. We have one more presenter.
Thank you.
Dimitri. And then we can have questions. You have to get out of the room. Not so long.
We need to find the presentation, actually.
He's not this man. So which one?
Yeah, this one. Yes.
Yeah, you have videos on there.
Yes.
Okay, it's fine.
Okay. Thanks everybody for coming. And I'm here from Innovative Solutions in Space, so-called ISIS, from Netherlands, and I'm a bit more involved in actual hardware delivery and launches. So I will try to explain a bit what, when you design your mission, after that you have to launch it, and it's a bit practical thing I'm going to explain. So first, a few words about ISIS itself. So it's a startup in Netherlands. It started to operate 13 years ago, and up to now we launched a number of satellites. We built ourselves around 100 satellites. Now the company is around 100 persons, and we launched under our manifest about 300 satellites. Most of them are CubeSats. One of them was microsatellite. Also, we have a number of satellites which are operated by ISIS right now. We commission them and we operate them. So it's tens of those satellites now. And also, the smallest CubeSats we launched were under 1 kilogram. The heaviest one was 25 kilogram. We operate a number of ground stations over the world. And also, ISIS is a company which may deliver complete solutions like mission. So if you have a mission in mind, you can come to ISIS and buy the mission design itself, and it would be delivered up to the moment you actually receive data. But also ISIS provides components and subsystems, and also we organize launches. Launches is actually what I'm involved most. So here is presentations what kind of launches or the number of launches we were involved or we were managing. And the recent two to the right is actually SL-23, which was launched 29th of November this year, with 3CAT-1 satellite together, and ISL-20 is SSOA mission with Falcon 9, which was launched 3rd of December this year. So both missions within 1 week actually. And the last one, ISL-24, is actually what is going on right now, and I will be going there right after this meeting for participation. So this is a short video. Basically, you heard a lot of CubeSat deployment in general, but Indian guys provided the possibility to actually see the what is going on in space. So basically, you can see CubeSats are deployed. It's on-board camera of PSLV C-37 mission, and you can see Planet spacecraft are deploying. You can see them tumbling because they have a flap which opens, and it opens after a satellite had been deployed. So it creates some disturbance, and you see that the satellites are tumbling. But also in the end of this video, you will see other satellites which do not have deployables. They releases quite in direction and no disturbances at all. So basically it was one of the missions, and why I put it in here, because it was world-breaking record with 104 satellites in one mission, of which 101 were under our manifest. So we were actually delivering hardware, and those satellites which you see deployed, they are actually under our manifest. The video is a bit long, so I will proceed. Okay, so should we? Just a second. I will show it maybe later. Basically, if we speak about CubeSats, so we kind of need to understand that it's a segment like below, usually below 10 kilograms. We are targeting now a bit higher range of masses, and also like there is a wide range of CubeSats. I will not go into details, but our target is like most of the time it's below 10 kilograms. So then, if you design the mission, it's very important to understand that in space you do not have really possibility to fix something. So it's a key point in here would be reliability of your satellite, of your mission. And like an illustration, recently Elon Musk sent Tesla in space. It was cool, it was nice, but it is useless. If we speak about mission, if we speak about launch, the claimed price per kilogram of launched mass, usually it's an advertisement everywhere, like we can do it for 20K, we can do it for something like 30K of euro, but in fact it's a much higher price. So if we speak about CubeSat mission, usually investors and money which put into this mission shall some way return, and it's like important to understand that it is important to make a satellite reliable, and your mission if it is launched and is not in use, it would be a real shame in this case. So a few aspects need to be also involved in the launch. First one is regulations. Like in general, by regulations we mean that general governance of a whole mission process or a whole satellite process. First of thing, in your country, you need to obtain a few licenses for being able to launch a satellite. First one is, of course, RTU, authorized frequency allocation, which we kind of discussed in very short. It's a relatively difficult process, and it should be clear that usually you have to apply for this frequency allocation, which you will operate your satellite well in advance. And why it is important, you can imagine that a few satellites are launched together or nearby, and they transmit their signals, they receive their signals, and if there is a clash, so it would be interference and maybe impossible to communicate to your satellite, which is not something you really want. Sometimes, like illustration, some smartphone, but in fact, it is possible to have your antenna receiver with such a high amplification that if someone transmits near you satellite with high power, and even your satellite is off, the antenna gain may be burnt out. So it's important to get this license in any case. It's one of the things. Next one is actually obtain permission to launch satellite. It's important to understand that after introduction of satellites, like a class of objects, the space in international there were established rules of using the space, and according to those rules, each country which launches a satellite is liable for any damage it may cause in space or in ground. So if something goes from space to a city and hits something, then the liability lays towards a country. So each country has to apply for, or while you want to launch a satellite, you have to apply to local country authorities to do it. In Netherlands, for instance, if you want to launch, you have you request for frequency allocation, and the same authority also authorize the launch itself. It is really dependent on country itself, so it's important to investigate this process in here, and of course it's important to do it in front, because if those licenses are not in place in time, then it may be quite difficult to launch a satellite, and even possible to withdraw it from a manifest. Then the last part of launch authorization is actually export process, because your satellite is a piece of very important or some way restricted hardware. It's important to get export license towards final destination. For instance, with Russian launches, it may be difficult now because of some reasons. For some other countries, it's also a kind of process. So basically, it is important to apply for export license for a satellite to be delivered to a launch base, and then it would be possible to launch. This is concerning regulations, and then we have like CubeSats. Launch itself involves like tons of payload, and CubeSats are usually a very little fraction of this payload. So it is important to understand that satellite is under development now, is actually co-passenger. So it also, like in a tram, you come together along with other people. So it's also important to understand that it's going to be launched together with other pilots. And especially for launch service providers, the guys who provide rocket itself, it is important to launch a rocket without any danger. So it is key word here would be safety, because they launch a rocket. It is involved millions of euro, and they really want to be sure that the satellite is not endangering anything in their rocket. So that's why they claim for some compliance. And just other explanation what is going on while launching a rocket. So basically, you drop it sometimes. So it's very rapid and very this process involves a lot of energy, which releases in a very short time. It's because right now we have only a way to reach space with combustion, with chemical reaction, with it converts into kinetic energy, but it is so condensed in time that you actually may compare it to explosion. So it's a very harsh environment. And if we speak about environments, so let's talk about this. So launch vehicles usually provide their requirements in terms of environments, and those environments are, it's the same slides. So it's like mechanical environment which your payload would experience during the launch. It may be thermal environment, pressure, humidity, electrical, something else, and so on. So basically, if we speak about mechanical environments, it's, for instance, steady state acceleration or static acceleration. What sources of those accelerations? You combust your fuel, you, according to Tsiolkovsky law, you go faster, and you accelerate. So this acceleration is, usually it's given in documents from launch service providers, like users' guides for rockets. Those figures usually are they may be variable from mission to mission, but in general, it's something you need to expect. And for instance, those figures are from Soyuz launch manual. So basically, you can expect up to 4 Gs in 5 Gs in one direction, and In lateral direction, it would be around 2 Gs. For other launch, for other rockets, it may be much harder. For instance, with Vega, you can expect up to 20 G. So in any case, static load accelerations, usually in our experience, are not such important for CubeSats, because it's a very condensed, very dense piece of hardware, and those static loads are not such important, but still you will have to comply to them. And your design also should be should take into account those loads. Then, like sine, also mechanical sine vibration, they have they may be low frequencies, but in a very long period. Like sources of those environments are usually transportation. So if you transport something, it vibrates, and it may be possible to figure out this as sine vibrations. Also, sine vibrations may occur in flight, like a structure itself or a rocket itself is working as a spring, actually. So basically, it's not really accelerating like very steady thing. So it may it's so-called pogo mode of rocket. So basically, it has sine vibration of low frequency, but a very high amplitude. So this also has to be taken into account, but in general. And the most important for CubeSats are actually the random vibrations, because random vibrations are very critical, especially for structure elements, joints, and also to electronics, because electronic components are small, but they are attached to PCBs. So with those random vibrations, it is possible to get loosen of those structural components or joints. And those are the most critical to small satellites. The origins of those loads are usually like a turbulence of air, which causes vibrations of rocket, or nozzle, like propulsion system work also with turbulence. This creates those loads. For Vega, for instance, those loads are really high, and like 20 G RMS. They usually not that high, but those are the most critical for satellites of our range. Then, of course, we have acoustics. Again, those loads are originated with also turbulence of air when we pass dense atmosphere, and also from nozzle work. So those levels are really high. They may be up to 140, 146 decibel. It's relative pressure. And for instance, the threshold of our hearing for some frequencies is around 50, 70 decibel. And pain, you will get pain of sound around 110, 120 decibel. So it's really high. And but for CubeSats, it's not such important, because the surfaces are very small, and those loads usually are important for for MLI, for multi-layer insulation, like covers or blankets which protect your satellite. But for CubeSats, it's not relevant. Also, those loads are important for some glass, like for solar panels, but solar panels now are much stronger. So those are not really important, and most of the time they may be emitted, and compliance may be done by compliance to random vibrations. So this is just an example. Another environmental variable is actually shock. Shock sources in a rocket usually is pyro devices. You have to separate huge objects, like stage may weight in the beginning of like 200 tons. and it shall be held together, but then after all fuel is combusted, you have to separate it. So you have to release those stages, and it involves a lot of energy again. And the source for this energy is pyro. So usually this is pyro spectrum, which you can kind of expect. And those shock loads sometimes are creating more problems than all other loads. So you have to take into account the shock loads. They depend on the vehicle and the place itself, so sometimes it's possible to relieve those loads a bit, but it's a long story. So then electrical environment. Depending on where you get, you may have problems with plugs and your equipment. Recent problem I had in India with soldering iron, which I burnt out because it was 110 hertz net intended to be used, but it's using 220. So it should be just taken into account while preparing your mission. Another thing is thermal. So this is actual picture of first Indian satellite, which was transported to launch base. So you need to be aware about what may happen to your satellite while it's transported, and you, if it's needed, you have to provide like a canister which will provide proper thermal ranges for your satellite during transportation before actual launch. Then pressure drop. It's important to understand that your satellite has trapped air inside and also vapors, so or water. In case we rapidly launch something into space, the pressure under payload fairing drops, and drops quite fast. Sometimes it may cause problems with if you have your PCBs and you have glue there, and there is trapped air or trapped water, so it's possible to have so-called popcorn effect when it's when vapor create layers of PCB coming out, and then it may go to big problems in your satellite. It may not work after. Then other aspect is actually electromagnetic compatibility. So launch vehicle has a lot of transmitters to transmit telemetry during the launch. And also it has some receivers. For instance, if something goes wrong, then ground crew may issue a signal to distract the launch vehicle. So for these reasons, they have requirements to not emit and not transmit in some frequencies. Usually for CubeSats, it's not very important because most of the times they are off during the launch, but still needs to be aware. Then we need to comply those all requirements, and the way to do it is actually we need to validate it. So we need to test. Usually it's done by tests. So for instance, tests are done in the echo chamber for electrical magnetic compatibility. It may be used acoustic test chamber, which is to the right. It's actually high power dynamics, which provide the required environment. It may be done in the thermal vacuum chamber or thermal chamber. It depends on the intended test. And then my favorite is actually sleeping table with to create a mechanical environment. So basically it's a solenoid with a huge coil, and you attach sleeping table or a platform to you put your equipment to this table, and then you create using some loop of control, you create the required envelope of environmental levels like sine vibration, or even it's possible to go to quasi-static it's not really quasi-static, but it's possible to simulate quasi-static loads with sine vibration. So it's some way you can transfer it. So basically, while doing this test, you confirm that your structure is integral, and of course, you have to have like a set of applicable factors or a set of pass-fail criteria. So you can say that your satellite, your system is passing or not the requirement. And for instance, one of the most important for like mechanical test is first natural mode of structure. So basically, it's important to have it outside some range, but also it is important to have it the same before and after test. Like if those frequencies changes, it means that damping ratio of your satellite goes different. It may mean that something in the satellite become loose or something is broken. Other criteria usually is like system should work actually after the tests. It's important to for you as a designer to set those requirements and to understand them and also to comply to those requirements. There is a bit of different philosophy in terms of CubeSat production. Like sometimes you can have two models. One would be used, they are equal in the beginning, but one of them is used for qualification. The qualification loads usually much higher, like or say a bit higher. But the second model would be tested only to acceptance. Those levels are much lower, and this means that your actual satellite, which will go to flight, will not experience very high loads and will not be over-tested, so it would not be weakened by tests themselves. Other philosophy is to use proto-flight approach. Is when you have budget only for one model, so you build this model, you test it to some loads which are higher. The model is a bit over-tested, but you design it the way that you're sure it will survive those tests and also further time in the mission. So like those two models. And of course, while performing the tests, it is important to understand that the test facility has to be like kind of certified, because the level you specified, they have to be the same what you will get after the or during the test. Because two options also available is that the test setup would be under-tested, and it would be not really compatible to the loads, or it is possible to over-test setup because test equipment was providing much higher loads than expected. So basically, certification means that the measurement sensors should be calibrated and the personnel should be trained at so on. So, and the last point is actually logistics, which is also very important. Like launch window or launch itself tend to sleep like a few months. Like if it is stated that the launch would occur this summer, in fact, our experience tells that it's not really true. So basically, average delays are about a few months, and it is important to understand that after satellite integration to a deployer, it would not be really accessible, so it's difficult to access it. Usually this integration takes place in our facilities with some other, it is for launch service providers, guys with rocket, it is much easier to work with so-called aggregators, because they have much more payload in one hands. They have one person or one set of one team to communicate with instead of multiple teams with their small satellites. So for launch service providers, it is easier to work with one partner, and So it is very difficult, almost impossible to have someone in the launch base performing some late tests of their equipment before it is installed to a rocket. So this is important logistics-wise, because if the launch is set for some period, so then before, ahead of this time, it would be integrated in a deployer, so-called, and then it would be transported to a launch site, and most of the time it will wait some period before actual launch. And during this time, it would not be possible to access satellite, to charge batteries. So it's important to design a satellite the way that it really do not require a lot of attention after it's integrated. So basically, I think that's it.
So we are open for questions now, since we're done, and I already showed my slides, so I don't have to talk. If you would like to ask our speakers any questions, then we can do that. If there's a question, you'll come up. I don't see a question yet. Are there any questions for our speakers? Yes? Hold on. I'll get back to you in a second. What's your, stand up, please. What's the question?
I would like to know what is the best way for us to get involved in the space industry after we graduate.
He wants to know how to get into the space industry once he graduates. That's a loaded question. Anybody care to answer? First, you need to graduate, okay?
Yes, definitely. Of course, I cannot talk for myself, okay, because I'm in the university, but I think I can say something for the students that, I mean, just graduated from our school. Let me say in simple words, they find their way, or sometimes the companies or the institutions find them, okay? When I say they find their way, is that in some cases they have started their own business, like this, small companies, 3 people trying to do something on their own way. Sometimes in the Barcelona area, the space industry is not very strong because of political reasons. Okay, traditionally, what was until the Spanish Civil War was there was aerospace industry or aeronautics industry in Barcelona, but then it was focused in Madrid and in Seville, not in Catalonia. But traditionally, in Catalonia, we always target to either Toulouse, which is 3 hours drive from Barcelona, or to Estec, okay, which is the, well, Estec and Esrin, the 2 main centers of the European Space Agency. Okay, so this is one way. And the other is, and I always encourage my students to publish, okay, when you are doing your PhD thesis, to publish and get the results published. I have seen people in the conference approaching me, has this student of yours come to this conference? Say, not, but he was in the other. I want to talk to him because what he did in his project and he published in that paper, we are running a project similar to this one, or we want to start something like this, you know, you like the idea and you want to implement it, we want to hire him. And that has happened. And right now, from my lab, we have 3 students at JPL, NASA. Not bad. Many others at Estec and other companies. So, I mean, even at ISIS, we do have former UPC students. At Gomez Space, we do have as well. At other companies in the Barcelona area. So, I mean, they found their way because of all these connections that you have during basically your work, okay, as a graduate student. And sometimes it's the other way around, that they contact because, I mean, they specifically want to hire a PhD student that has been developing this or that technique that is very specific. But it works.
Maybe a few more words about that. I have 2 answers, one short and simple, and others a bit difficult. First one is simple and short. ISIS is hiring all the time. So check the ISIS web page. And the second one is actually, we did discuss it yesterday in a bit, that the satellite industry up to some moment, it was very closed, very restricted. And it was up to the moment actually CubeSat standard was introduced. Because with a CubeSat standard, it became possible for very small teams to build their missions, to build their satellites, and to send them to space with limited budget. Because with huge satellites, you can imagine that if a satellite costs like tens of million euro, it's very difficult to obtain this budget. But with small teams, if you have ideas, you can approach people like investors, like people who are interested in science, in technology, in your mission. So if you have ideas, there is a way to actually go to a space industry with those ideas now. So it's a bit long, but it's also possible. Yeah, that's it.
Thank you. Okay, so I'll add to that. In this project, you can get your diploma, and you can publish. We do that. We do that. We have undergraduates publish. Any other questions, please?
Nije pitanje, ali
Okay, good.
mali model, dakle dummy CubeSat, da ljudi koji dođu na naša predavanja dobiju dojam kako to izgleda. Dakle, kad vi kažete 10 puta 10 cm, ok, to je jedan kubični decimetar, ali otprilike kako to izgleda kada je to pripremljeno za orbitu ovu našu.
Dajte da ga ovdje stavimo da se vide.
Dakle, ovo je recimo VHF, UHF.
I nema 1 kilu. Nema kile. Teži je inače, tako? Ne moramo. Da, samo od stakla je. S vanjske strane je staklo, jel da? Ima još kakvo pitanje? You can take this.
Hi, hello. I have a question for Dimitri from ISS. You said that launch vehicles are sending telemetry to the ground while launching. Could you please tell me what are the information that are sent and what are the communication bandwidths and the speeds, if you know that information?
About communication bands, I'm not really quite sure, because it also depends on launch vehicle itself. But what kind of information is sent also depends on launch vehicle. With Soyuz, for instance, they transmit like our telemetry as well. So basically, it's time of deployment and particular door opening. They transmit information about their control system, about pitch, your trajectory measurements. They transmit information if something deployed or not. With Indian launch vehicle, they transmit even live video stream, and I can show one like from a recent launch. They actually transmitted live video picture of deployment of satellites. And not a while ago, they had a bit of bad luck with their launch. They launched a rocket, all went as expected, except the payload fairing separation. So the satellite was actually deployed inside the payload fairing, and it was possible to see in the screen in the control room. But they actually transmit quite a lot of information, especially trajectory measurements. And of course, they transmit some kind of restricted information about what each system does, because basically, if something is off nominal, of course, you have to make a decision if it's going well or not. So in general, if I understand you right, it's not really publicly available information. Like it's not possible to take it and then kind of understand what is going on. You can get the reception, but you will not uncode it. It would be.
Can you sometimes decide not to launch if something is wrong with the modules?
Yes. Recently we had Falcon 9 launch with number of CubeSats, and they postponed this launch quite a number of times. Some of those times were related to actually not readiness of Falcon launcher itself. Sometimes it's related to the payload, so they have a number of parameters of main payload, and they may go or not go with a launch. This decision may be done a recent attempt of Delta Heavy launch was a day ago, and they didn't really launch a rocket because something was not right with payload. So they made a cross-check. They found out that it's not nominal, and they stopped the launch 7 seconds prior to the launch itself. Yeah, that's.
Thank you. This meeting is over. The speakers. I said the meeting is over. We can continue outside. I think the room is booked. Thank you.